Return on investment is the single most important metric for any fiber-to-the-home project. Companies invest vast sums of capital upfront. They spend millions on digging trenches. They spend millions on laying cable. They spend millions on installing equipment. This money is spent long before the first customer is connected. Revenue arrives much later, one subscription at a time. The entire business case rests on a delicate balance. The cost of the build must be recouped by future customer payments. A small shift in costs or a slight delay in customer signups can dramatically alter the profitability of a network. The goal is simple: lower the initial cost, increase the take-up rate, build the network faster. The first major decision in any FTTH rollout is where to build. Building everywhere at once is financially impossible for most operators. They must prioritize specific towns, districts, or even streets. Traditionally, this decision was based on broad demographic data and competitive analysis. AI brings a new level of granularity and accuracy: demand forecasting. It lets operators pinpoint potential customers with surgical precision. The system ingests a wide variety of data inputs: detailed population density maps, property types, average household income levels, existing internet service usage from billing records, local business activity, new housing developments. Machine learning models get to work. Random forests, gradient boosting. They learn from past rollouts what combination of factors predicts success. The output: a heat map of the entire region. Scores down to individual buildings on likelihood to subscribe. Planners focus marketing and construction where ROI will be highest and fastest. Far more efficient than blanket marketing or speculative builds. Consider a practical example. A large city with diverse neighborhoods. An AI model flags a small, overlooked suburb. High concentration of remote workers, rising property values, only one slow, legacy internet provider. AI predicts 45% take-up in year 1 versus 25% city average. Operator prioritizes that suburb for initial rollout. After deciding where to build, the next challenge is figuring out how to build. This involves designing the physical routes for the fiber optic cables. This is an incredibly complex puzzle. The goal is to connect every targeted home and every targeted business in the most cost-effective way possible. The routes must navigate around obstacles like major roads, rivers, parks, historical buildings. Planners must decide whether to use existing underground ducts, utility poles, or dig expensive new trenches. Every meter of cable and every hour of labor adds to the cost. AI can automate and optimize this entire route design process, saving enormous amounts of time and money. The AI system begins by consuming multiple layers of geospatial data: high-resolution satellite imagery, detailed street maps, utility company records showing existing ducts and pipes, land parcel data indicating public versus private property. Specialized algorithms then go to work on this digital landscape. Genetic algorithms, reinforcement learning, can explore millions of potential route combinations in a matter of hours. They test different paths and evaluate each one against predefined cost parameters. The system learns to favor routes that maximize use of existing infrastructure and minimize new trenching, the most expensive part of any build. For instance, imagine an AI designing a network for a dense urban block. It analyzes GIS data and discovers underutilized old telecommunications ducts. A human planner might have missed or skipped that. The AI quickly designs a topology that routes 70% of the required fiber through existing ducts. This avoids digging up busy streets, which would have required expensive permits, traffic management, and night work. The AI presents a handful of optimized route plans, each with a detailed cost breakdown and a list of potential construction challenges, allowing the human design team to make a quick, informed choice. Furthermore, advanced AI techniques like graph neural networks can learn from the successes and failures of past projects. By analyzing thousands of previous network designs and their final construction costs, these models learn what makes designs cheap to build and easy to maintain. They can suggest topologies that are low-cost, more resilient with built-in redundancy to reduce the impact of any future cable cuts. A fiber project's budget is its lifeline. Inaccurate cost estimates at the beginning of a project can lead to disastrous consequences later on. If costs are underestimated, the project can run out of money halfway through construction. If they are overestimated, a potentially profitable project might never get approved in the first place. AI can significantly improve the accuracy and speed of feasibility studies and cost estimation. It does this by integrating a far wider range of data points than is possible with manual methods, providing a more holistic and realistic view of the potential expenses and obstacles that lie ahead. The AI models for cost estimation are incredibly sophisticated. They take the optimized raw designs as one input, then they layer on many other types of data. Geological surveys that indicate soil type, helping to predict whether crews will encounter soft dirt or hard rock. Localized labor cost data. Current market prices for fiber cable and equipment, terrain data from satellite elevation maps. By combining all these factors, the AI can generate a detailed line-by-line cost forecast for each proposed network segment. This moves beyond simple per-meter cost averages and provides a much more granular and defensible budget. A key innovation in this area is the use of natural language processing. Every town and city has its own set of rules, regulations, and permitting processes for construction. Manually reviewing hundreds of pages is slow and error-prone. An NLP-powered AI can scan these documents in seconds. It can automatically identify key requirements such as special environmental assessments, specific traffic management plans, long lead time permits for crossing railways or major highways. For example, an AI could flag a new moratorium on street cutting in a business district, alerting planners to reroute or delay that section. This comprehensive approach greatly reduces the chance of unexpected costs. The budget is not just a guess, it is a data-backed forecast. When the AI model flags a high-risk area, boring under a river, removing protected trees, the planners can allocate a specific contingency fund. This level of detail gives investors much greater confidence, making the project more bankable. Building a fiber network is not just about connecting today's customers, it is about building a piece of infrastructure that will last for decades. This means the network must have enough capacity to handle the traffic demands of the future. If the network is under-provisioned, it will require expensive and disruptive upgrades in just a few years. If it is over-provisioned, the operator wastes capital on unused fiber and equipment. AI helps operators strike the right balance through intelligent network capacity planning, ensuring the network is built right the first time. This involves making critical decisions about network architecture, such as split ratios, fiber counts. AI models can analyze current internet usage trends and project them far into the future. The growth of video streaming, the rise of cloud gaming, the adoption of virtual and augmented reality, the increasing number of connected devices in the average home. By simulating network traffic over a 5-year horizon, 10-year horizon, or even 20-year horizon, these models can predict future bandwidth requirements for different parts of the network. This allows planners to make informed decisions about the core architecture. For example, a residential area may be fine with a 1:32 split, but a growing business district may need 1:8 to handle higher uplink traffic. This foresight prevents costly future upgrades. Imagine a planner installs a 144 count fiber to serve a new subdivision. 5 years later, demand explodes and the cable is at full capacity. Digging streets again to install a second cable becomes necessary. An AI model might have predicted this growth and recommended a 288 count cable from the start. The incremental cost then is minimal compared to a massive future upgrade. AI also assists in the optimal placement of key network facilities, the location of central offices, cabinets, major splice points. By analyzing the demand map and optimized routes, AI determines the most efficient locations for these elements. The goal is to minimize the total length of fiber while ensuring easy, logical expansion. As the community grows, the network can grow with it smoothly and cost-effectively, building a future-proof asset. Not just a present-day service, you know. The role of AI does not end once the plans are finalized. It continues to provide significant value during construction and through the network's operational life. During the build, AI acts as a sophisticated project management tool, dynamic scheduling of construction crews, delivery of materials, management of permits. By creating an optimized workflow, AI can reduce idle time for expensive machinery and for specialized labor. If an unexpected delay occurs in one area, the AI can instantly recalculate the master schedule and redeploy crews to another part of the project. Once the network is built and customers are connected, AI shifts into monitoring and maintenance. The network includes active electronics and passive fiber optic cables. Faults can and do occur. AI-powered monitoring systems analyze performance data in real time. They can detect subtle anomalies, like a degrading optical signal or equipment starting to overheat. That enables predictive maintenance. Rather than waiting for failures, the system can automatically create a work ticket and schedule a technician during a planned window. This proactive approach improves customer satisfaction by reducing downtime. A customer fixed before they notice a problem is much happier and more loyal. Planned visits beat emergency night crews. Continuous monitoring data creates a powerful feedback loop. Field insights, like a splice enclosure showing higher loss in cold weather, feed back to the AI. Next rollout, the model flags that part as a risk or recommends an alternative. The cycle of planning, building, monitoring, learning ensures operators get progressively better and more efficient. While AI offers transformative potential for FTTH planning, it is not a magic solution without its own set of risks and challenges. Adopting these tools requires a clear-eyed understanding of their limitations and a strategy for mitigating potential problems. The most significant risk is data quality. AI models are only as good as the data they are trained on. Garbage in, garbage out. If the GIS data is outdated, if customer addresses are incorrect, or if the cost data is inaccurate, the AI's output will be flawed. Like designing a route through a new building, not on the map. Operators must make data governance a top priority, invest in resources to collect, clean, and continuously update core datasets. Create processes to validate information and fix inconsistencies. Start with a small, well-defined pilot. Build a high-quality dataset for a manageable area before scaling. Another major risk is algorithmic bias. Models trained only on historical data can replicate inequalities, favoring wealthy neighborhoods, ignoring lower income or rural areas, creating a digital divide. Human oversight is essential. Planners should set policy-based rules. For example, requiring a percentage of builds to serve designated underserved communities, regardless of short-term ROI. There's also the risk of over-reliance and tool costs. AI aids, but does not replace human expertise and judgment. Local planners hold on-the-ground knowledge no dataset captures. Politics, relationships, unwritten rules. Start with accessible cloud-based AI services or open-source tools to prove value before committing to enterprise-grade solutions. Adopting an AI-driven approach to FTTH planning may seem daunting, but it can be undertaken through a clear, methodical, and phased process. Flowchart: set ROI goals, gather and clean data, run pilot, combine AI and human experts, measure, scale up. For any network operator, the journey begins with a clear business objective. It is not enough to simply use AI. The goal must be specific and measurable. For example, target: reduce civil construction costs by 15%. Or target: increase first-year take-up by 10%. These concrete targets guide implementation and provide a benchmark. Without a clear ROI, the project will lack focus. Start small with a pilot. Choose a town or a few neighborhoods. Keep scope manageable. Focus on gathering and cleaning internal data, customer lists, billing, and external data, GIS layers, satellite imagery, census records. The pilot is a learning experience. Data engineers refine pipelines, AI specialists build and tune demand forecasting and route design models. Collaboration is key. Assemble AI experts, data scientists, network planners, engineers, and legal experts. The AI produces outputs. Humans validate. Planners check routes against terrain. Legal reviews permits. A human in the loop ensures recommendations are practical and compliant and builds trust. Measure rigorously. Lower build cost, better initial area selection, fewer surprises. Quantify improvements to build a business case to scale. If results are positive, invest to scale and make AI a core component of future FTTH planning. Return on investment is and will always be the driving force behind fiber-to-the-home deployments. The financial stakes are simply too high for it to be otherwise. Artificial intelligence provides a powerful suite of tools to strengthen the business case. It is not a magical black box, but a practical application of data science that delivers tangible benefits. It enables smarter demand forecasting. It automates route design, cheapest paths. It automates route design, fastest paths. It delivers more accurate cost estimates to prevent budget overruns. These advantages compound. Build the right-sized network for future growth. Monitor for proactive maintenance. Lower initial capital expenditure. Lower long-term operational costs. The result is a project that reaches profitability faster and delivers a higher overall return on investment. Approach AI adoption with a clear strategy. Start with a specific ROI goal. Build a high-quality data foundation. Test on a small pilot project. Most importantly, foster a culture of collaboration. AI specialists and seasoned industry experts working together, combining machine intelligence and human experience. The human role remains absolutely vital. AI handles massive-scale processing, freeing planners for strategy, community engagement, complex problem-solving, and final decision-making. The goal is not to replace planners but to empower them, augmenting human intelligence. This partnership ensures plans are analytically sound, practically achievable, ethically responsible, making sure underserved communities are included. In modern telecommunications, efficiency is paramount. The operators who plan and build faster, cheaper, with greater precision will win. AI is a critical enabler, de-risking multi-million-dollar investments and increasing the probability of success.